Um, so the mathematics required for physics in our time now includes not only the mathematics of the 19th century, but also general relativity, the mathematics of tensors, general relativity, and the mathematics of quantum mechanics, which in particular brought in path integrals. And so I'm going to talk about path integrals today. Also, as you know, there's no final exam. So instead of a final exam, I'm going to give a lecture on Tuesday, the 13th at 5:30, not 5 o'clock, 5:30. That's the official exam time. So instead of an exam, I'm going to Zoom a lecture at 5:30 next Tuesday. Right now, though, I'm going to flip back to the beginning of the chapter on chapter 20 in the book on path integrals. And path integrals are associated with the name Feynman, and quite appropriately so. I'm looking for my Apple Pencil. Here it is. They, I think, were known to some extent by Dirac, and to some extent by Schwinger, but it was Feynman who really appreciated their significance and made them a serious part of physics and a tool in his discoveries of physics. So I'm going to be talking about path integrals today. Let me just cut this back a bit there. Okay. So the mathematics that goes into these path integrals is based on two Gaussian integrals. The first is the imaginary Gaussian integral, where you have e to the I, a being real, b also real, e to the I a x squared plus 2i bx. And that gives us this expression here. That's the actual integral. It's an integral that we did back in chapter 6. That integral is a little bit surprising because all the factors, it's an integral of phase factors. And you might say, well, how is it that we got something finite when we integrate over an infinite range? The reason is that this, you have here e to the I a x squared with a not equal to 0. If a is equal to 0, it's a delta function, which isn't really, of course, a function. It's a functional, a map from functions to numbers. The other thing on which path integrals are based is the standard, Gaussian integral, where a has a positive real part. And so this is the traditional Gaussian integral, where you just get e to the minus b squared over a times square root of pi over a. So these are the two basic integrals on which path integrals are based. And they can be generalized from one variable x to n variables x1 through xn, and there instead of e to the I ax squared, you have a quadratic form, and here the idea is that S is a matrix that is it's obviously symmetric, it has to be real, and real because A is real in the first integral, and what one has here then is a real symmetric matrix that has to be non-zero, non-singular. And the reason it has to be non-singular is, suppose that it had 0 as a determinant, then there'd be a linear combination of x, there'd be a linear combination of x's that S could map to 0. And in that case, part of this integral would be free of the quadratic dependence on x. You just have a 0 here in the exponent, and this would then give you a delta function. Equivalently, you can just say, well, assume it's non-singular. What do we get as an answer? Well, we get something with the determinant in the denominator and S inverse up here. And so you can see that it had better be non-singular, otherwise you get the wrong, you just get nonsense. The traditional Gaussian integral gives us this expression here, where again we require that S be non-singular, be a non-singular matrix. And then that multiple integral is involves a determinant of S and the inverse of S. So these are the basic mathematical ingredients that go into path integrals. These are the simpler and obvious, well, not obvious, but they're the simpler elementary bases of path integrals. The more sophisticated, but certainly intuitively plausible formula is one that's associated with the name Trotter, and it's called the Trotter product formula, which was published back in 1959. It's of the following form: the exponential of a plus b is the limit as n goes to infinity of e to the a over n times e to the b over n raised to the nth power. Now here, you might say, well, this is an arithmetic identity. The point here is that A and B are matrices, and so A and B are matrices, and so this is a non-trivial relation, but it's intuitively plausible. And here's the way it's used in the derivation of path integrals. Let's look at the Boltzmann case first. If the Hamiltonian H is a kinetic part plus a potential part, then the Boltzmann operator is e to the minus beta k plus v. Here, beta is traditionally, here, let me just write it more clearly, is 1 over Boltzmann's constant times the absolute temperature. And what one can, the Trotter product formula then expresses this exponential as the limit as n goes to infinity of the nth power of the product of e to the beta k over n, e to the minus beta v over n. And as I said, it's intuitively plausible. and in fact is mathematically correct. The the other form, the time evolution form, as opposed to the Boltzmann form, is e to the minus I t h, h being k plus v, divided by h bar, and that is this expression here. And you can see that this is a little bit trickier, because not only is it all phase factors that are unimodular, but also in the denominator here is a very small number, h bar. And so you really have to seriously take n going to infinity. So let's consider path integrals in quantum mechanics. They can represent matrix elements of the time evolution operator, which of course is e to the minus ih, the Hamiltonian divided by h bar, and then the time interval. And to keep the notation as simple as possible, I want to use a one-dimensional quantum mechanics in one-dimensional Hamiltonian p squared over 2m, non-relativistic. So we've jumped from general relativity through special relativity down to non-relativistic physics for this particular example. And what we want then is the one-dimensional non-relativistic Hamiltonian for a particle of mass m moving in a potential v. And Q and P are position and momentum operators. They obey, of course, the standard commutation relation. QP is IH bar. In case somebody doesn't know what that means, here QP is QP minus PQ equals IH bar. Okay. So I think maybe I'm going to switch the color now to something that is a little more visible. So these are in ordinary quantum mechanics, Q and P, of course, are Hermitian operators that have complete sets of eigenstates and eigenvalues. Q prime runs from minus infinity to plus infinity. We're all real numbers, and the same for P prime. And you can see why it is that I emphasized completeness when talking about differential equations a couple of months ago, namely that it's the basis of quantum mechanics that you have Hermitian operators that have complete sets of eigenstates. And the sense in which they're complete is that if you integrate over outer products of position eigenstates or momentum eigenstates, you get the identity operator. And as you've no doubt learned in quantum mechanics class, the inner product of a position eigenstate with a momentum eigenstate is a phase factor divided by this square root. So to proceed, what we're going to do is use the Trotter product formula. So we're going to take this interval TB minus TA, and we're going to divide by n and call that epsilon. I'm going to write the Hamiltonian divided by h bar as little k for p squared. I'm going to abbreviate p squared over 2mh bar as little k, and I'm going to represent the potential divided by h bar as little v. And so then the Trotter formula is going to be then the time evolution operator then is e to the minus I time difference times little k plus little v. And the Trotter product formula says, well, you can write that as n factors of e to the minus I epsilon k, e to the minus I epsilon v, where epsilon is the time interval divided by n, and we're going to let n go to infinity. So we're going to write this in this way. And as I once said to you, probably more than once, to make progress in mathematics and physics, one often has to take 1-2 steps backwards before going forwards. And of course, this looks like a giant step backwards. Now, the reason for doing this is that we can evaluate these things between eigenstates Q and P of the position operator Q by inserting the identity operator in terms of an integral of outer products of momentum eigenstates like this. And if we do, well, the point here is you see that this is an eigenstate of Q. So we've got this thing computed. This just turns into V of QA, Q sub A. And over here we have an eigenstate of P, and consequently this just becomes P prime squared over 2mh bar. And so this little thing here is in fact equal to these two expressions. So in other words, here you see there's no way we can insert the identity operator in the form of an outer product of P states because there's no between here. Whereas if we write it this way in the Trotter product formula, then we have n different betweens. We can stick it between these two, between these two, between these two, between these two, and so forth. There are n different possibilities. And once we've done that, then this matrix element becomes an actual integral over just numbers. And so we have an integral over P prime, and P prime occurs here, and we have a Q there, and we're integrating over P prime, not Q. And the P prime integral is just a Gaussian integral. But of course, we've also got these factors that we have to consider. And these factors are given by these inner products. And so what we have here is the inner product of Q1 with P prime and the inner product of P prime with QA. And if you work them out, they turn out to be this phase factor. The QA, the VQA just comes out front because we're not integrating yet over Q, and we just do the P prime integration. We use then the Gaussian formula, the imaginary Gaussian formula, and 20.10. And what do we get? Well, explicitly, we have this integral where I'm using a cute notation here where I'm saying Q1 minus QA is this tiny interval of time, epsilon times QA dot, where epsilon is, of course, was defined earlier as the time interval divided by the integer n, which is going to infinity. And so in these terms, then, this P prime integral, without the prime at least, is given by this. And doing that integral, we simply get, well, this is the integral we're using. So this is the integral 20.1 with A and B and so forth replaced by the appropriate things. A is minus epsilon over 2mh bar. B is epsilon q dot over 2h bar. And if we do that, the original integral 20.1 takes this form, which is what we have here. And the answer, of course, is this, this phase factor. And so what we get from here is we get this prefactor is still here. This factor is still there. This integral gives us, it is this integral, which by this formula gives us this. So, so we've done 1/n of the work, but of course we have to let n go to infinity, so we haven't really gotten very far. But this is what we get for the first element of the Trotter product formula, the first factor in the Trotter product. God, is a tongue tire. Yeah, I guess it is a tongue tire. Anyway, so what we have then is the first element is this prefactor and this exponential. And the exponential, you see, is a kinetic energy, an element of kinetic energy minus an element of potential energy. And that, in fact, is an element of action. You might say, well, this was Q1 and QA. I see QA, where's Q1? Well, Q1 is hidden in that QA dot squared. Well, QA dot is Q1 minus QA over the time interval, the tiny time interval epsilon. The next thing you do is you put in another Trotter factor, and so you've got two Trotter factors, and you put in a complete set of position eigenstates, and you do the integral. Well, each one, we've just seen, each one is Q1 dot squared minus V of Q1. The other one is QA dot squared minus V of QA. And Q1 dot is Q2 minus Q1, where Q1 is the intermediate position. And so at that point, you have this integral. Now, this integral isn't so obvious because Q1 occurs in several places. It occurs in this potential. It occurs here in Q1 dot. And it occurs here in QA dot, because QA dot is Q1 minus QA over epsilon. So now what we do is we stitch together n of these, and so we have n integrals over outer products of q's, and each factor gives us a term like this, and so we have a sum of a bunch of terms. Each one is of the form the potential evaluated at some position q, and then the kinetic energy given by the difference of the two q's divided by epsilon, and then a prefactor. And what you can then see is that this is an element of a Lagrangian, and in the sense that L sub j is mqj dot squared over 2 minus v of qj. And you then have to integrate, though, over all the q's. And what we say then is that we write that whole thing, including the prefactor, in this way, as capital D of q hides the infinite number of dq integrations, and the prefactor, that's all capital D of q. And so the amplitude is given by this path integral, where the phase is e to the I, classical action over h bar. And it's a classical action for this arbitrary path q. It's not a classical path, it's an arbitrary path. So that's the path integral for one-dimensional quantum mechanics. You take the action being an integral of a Lagrangian from the first time TA to the last time TB, and it's m over 2 q dot squared minus v of q, and q of t is the path. And now what we see is this path is, we have to integrate over arbitrary paths, because we have been integrating over all of these intermediate positions. So in other words, the idea is that you're going here from some point q sub a to some point q sub b, and one path is, like this, and then another path, let me try to get a different color. Another path will be like that, and then you'll have a path that does this, and then let's see, I can do a green one. Then you have a path that'll do that. And so, and heck, we can even do a black path. And you have to integrate over all paths. And this seems hopeless, but it's well, in some cases it is hopeless, but in general, but we can still make some progress and can understand what's going on. This dq, the formula for it is, it's the product of all those prefactors times all the integrations that we're doing, dq1 up to dqn minus 1. This is for n integrals. And what we can do is we can also integrate over qa and qb and the outer products, and then what we get is the total unitary operator here. And in 3 dimensions, it's the same business. It's just that instead of q, you have a 3-vector q. So you have an integral of the kinetic energy minus the potential energy over time, but you integrate it over all paths of, over all 3-vector paths, over all paths in 3-dimensional space, and then you have an overall prefactor. Now you might wonder, what about that prefactor? Well, often you arrange things so that the prefactors cancel. Let's just see what we've learned so far. So the amplitude then is an integral over all paths of a phase, and the phase is e to the I classical action of the particular path divided by h bar. And so let's first consider a macroscopic process, and let's suppose then that to go from QA to QB, that there is a path that's classical. Now, for arbitrary QA and QB, there's not necessarily going to be a classical path. But in most cases, I suppose there is, at least classically, non-relativistically. Relativistically, there's less, there are fewer paths, because you can't have paths. Suppose QA and QB are really far apart and the time interval is short. Well, there's always a classical path non-relativistically. You just draw a vector from one position to the other, and you just go at sufficiently high speed to go from one position to the other. And there's always a classical path non-relativistically. But relativistically, well, you can't go faster than the speed of light. So there's a cutoff. And that's an interesting difference. that comes in just with special relativity. Anyway, let's get back to ordinary classical physics. I'm sorry, ordinary quantum mechanics, non-relativistic quantum mechanics. And let's suppose that there is a classical path. And as I said, there almost always is a classical path in non-relativistic physics. And the classical path, of course, is one in which if you follow the classical path, then deviations, the classical action is stationary. That's the principle of stationary action. And so what that means is that if if you consider the classical path, then there are a gazillion paths that are very close to the classical path. And all of these paths have almost the same action because the action is stationary. And so if you make very tiny changes, in other words, there are infinitely many paths that are arbitrarily close to the classical path, and the difference in the action is zippo because the action is stationary. And the result is that if you look at that path integral, and there it is, if you have the amplitude for the classical path is huge because it has all contributions will add with almost the same phase for all the gazillion paths that are only infinitesimally different from the classical path. So that tells us then that non-relativistic quantum mechanics tells us that classical physics is the limit. Classical physics is given by the principle of stationary action. In other words, paths that have classical actions that are stationary are going to be dominant macroscopically. And why did I say macroscopically? Because in a macroscopic path, this action is going to be big compared to h bar. And that's something I should have mentioned earlier, namely that if you have a macroscopic path and you consider the paths that deviate from a non-classical path, a path that's not stationary, then because this path has an action that's a gazillion times h bar, in other words, it's macroscopic, so it's a path that has an action that's a gazillion times h bar, that and it's not a stationary path, then as you vary from that path, you're going to get huge changes of phase, and they're going to cancel. So that's how things work for macroscopic processes. So for macroscopic physics then is governed by the principle of stationary action, and that's a consequence of path integration. And now suppose instead we consider microscopic processes. Well, if you have a microscopic process, then this action here, or equivalently, this action written as a path integral, this is going to be tiny because it's microscopic. So it doesn't matter whether the path is classical or not, because the difference in phase between two microscopic processes is going to be microscopic. And what the conclusion then is that in quantum mechanics, the things that can happen are much more varied than in macroscopic processes. So macroscopic processes are governed by classical physics, by the principle of stationary action. Microscopic processes are totally free, and on a microscopic scale, anything can happen that doesn't violate some conservation law. So that's what I'm saying basically here. If you have several particles, then the integral it's a path integral over all the particles, And it's the action of all the particles divided by h bar times I, and e to the exponential of that. And the non-relativistic action then is the sum of all the kinetic terms, all the squared velocities times the masses divided by 2, minus the total potential energy of their interactions. And so that's what you get. For a free particle, the potential is 0, and this integral is simpler to do. You have basically the Trotter product formula gives us this expression here. If we do the first integral over Q1, you see Q1 occurs here and there. And if you multiply this out, apply the Gaussian integral formula, which is that, what you find is you get this as an answer. And I'm a little puzzled as to why there are 2 2s. Oh, I guess it's true. All right. This apparently is the correct number here. Very strange, though. So let me just check that. Not now, but later. So doing the Q1 integral, we get this. If we do the Q2 integral, now we have Q3 minus Q2, and it's the same business, but now instead of Q2 minus QA squared, you get Q3 minus QA squared. And we're supposed to divide by 3 epsilon here. If you do all the integrals in this way, what happens is that you eventually have n epsilon, and you have, instead of Q3 minus QA, you have QB minus QA squared. And what is that? Well, that's the squared difference divided by the time interval times IM over 2h bar, and then exponentiated. And this is the standard form that you get in quantum mechanics when you ask what is for a free particle, what is that amplitude? And the way you calculate it in ordinary quantum mechanics is you say, well, QB e to the minus I, I'm just going to write this as capital T over h bar, p squared over 2m QA, you insert a complete set of states, and so then you have an integral dp, and you have the phase factors, and that's basically e to the IP. So I'm going to write this in I'm going to leave out all the factors. Those are the 2 phase factors, minus I p squared t over h bar 2m. Essentially, that is the integral, and that integral then gives you this expression here. Again, so in other words, you can apply, in this case, you can apply the formula 20.1 immediately, and you get that integral. In 3 dimensions, the amplitude for a free particle to go from Q0 to QT is QT. Why is that QT? Well, all right, my notation's a little weird here. Anyway, that's the correct answer. So by the way, this reminds me of a story I heard about Feynman years ago, maybe 50 years ago. He decided he was going to teach quantum mechanics, elementary quantum mechanics, graduate or advanced undergraduate quantum mechanics. He was going to teach it using path integrals. And so he started out on day 1, day 2, day 3, lecture 3. But after a few lectures, he decided that the teaching all of quantum mechanics in terms of path integrals was just hopeless, and so he too time consuming, and so he went back to the standard approach. So in other words, path integrals are wonderful for understanding and useful for some computations, but they're not ideal for everything in physics or in quantum mechanics. One case where they do work very well is when the action is quadratic. And the reason for this is that if you consider the classical path plus a deviation from the classical path, x of t is going to be a deviation. Well, then the classical action is going to be an integral of q dot squared, and q dot squared is going to be q classical dot squared plus x dot squared. And the potential energy is going to be V. The potential energy at time t is going to be V of the classical position at time t plus the deviation at time t. And now if you work that out, this square is just this. And if you calculate this in a Taylor series, you get a first term, a second term, all an infinite sequence of terms. But if the thing is quadratic, then I must say, I don't quite understand why I had so many terms here. Anyway, if it's quadratic, then these terms will all vanish. And so this integral is first the classical integral, and then the change due to the deviation. The change due to the deviation is the x dot squared minus b double prime x squared, and then all these extra terms here. Oh yes, you might say, why is it that that this thing is simplified? Well, the reason is that in the classical path, mq dot is minus v prime at q classical, and I must say I'm a little puzzled as to where the dot went. All right, well, let me just, because it's the classical path, this thing cancels and simplifies to this, but I must say I'm a little puzzled as to what happened that I got this x dot to cancel this term here. So I'm going to have to think about that. In any event, the bottom line is that the integral of the classical action plus a detour for quadratic actions is a term like this. And here SC is the S of QC is the action of the classical path, and then the detour is involved. This is the action of the detour, which is all of this. And what one finds then is that this correction to the action is independent of the classical path. And because it's independent of the classical path, what one has then is that the actual amplitude is this integral, which is, you see, you see, this thing is a constant dependent on the classical path. And so it comes out of the path integral, and what's left is the integral of the deviation. And I see I have a typo in 20.32. So basically, for a quadratic theory, the quantum amplitude is the classical phase times something that's independent of the classical path. And more generally, for theory that's just quadratic in the quantum variables, the total amplitude is the phase of the classical action times something that is independent of the classical path. And so for several particles in 3 dimensions, the same thing is true. In particular, a free particle going from one position to another is given by, this is the classical path, it's just a straight line. The classical action then is given by this, and the quadratic, then the formula for an arbitrary quadratic theory then is this phase times something that is independent of the classical path. Okay, well, anyway, what I said to you earlier was that path integrals are very good for understanding some things, and one thing in particular is the Bohm-Aharonov effect. And here, what we're talking about is a charged particle moving in an electromagnetic field, although the electromagnetic field is such that it's, in this particular case, it's just a magnetic field confined absolutely to a solenoid. So you have a situation where you have a non-trivial magnetic field in a pipe, but no magnetic field outside the pipe, because the pipe is made of a material that really absorbs the magnetic field. And now we're thinking of the classical action going from one point to another in the vicinity of that pipe. And in particular, the idea is that you've got the pipe here, B not equal to 0. And then you've got possible paths like this and like that. And you can go around the cylinder in 2 different ways. And the charged particle is going to have charge E, has never enters the magnetic field. It just goes around the solenoid. So I'm going to make this a very thick solenoid here. Maybe I'll switch to a different color. Now, what's the action? Well, the action here is the non-relativistic kinetic energy term minus the potential energy, and the potential energy here, I guess it's an electron, so charge minus E, but there was a minus sign here. And it's basically AI, JI, and that turns into AI, QI dot. So this is the current term, and that Q dot dt is just dq, and Q dot times dt is also dq. So the whole thing looks like that. I don't know if one has to we don't need to actually use this. Yeah, we do. We will use this, I think. So this action is quadratic and in Q and Q dot, and so the amplitude is basically the phase of the classical action times something that's insensitive to the classical path. And so you can then consider two different paths, and this path, for example, differs from this path, and the difference is essentially an integral, is essentially the integral of a path once around the solenoid. And so what you have there is this term plus an integral of a dot dq, and of course the integral of a dot dl or dq is equal to the integral of the curl of a dot d sigma or dA, and that's the integral of b dot d sigma, say, and that of course is what we call the flux. And so this thing is the E times the flux over H bar, where phi is the magnetic, capital Phi is the magnetic flux through the cylinder. And so this was proposed by Aharonov and Bohm, and eventually people did the experiment and showed that in fact they were absolutely right. And I think the thing to appreciate here is that this was quite a long time ago. This was like in the 1950s or probably the 1950s, conceivably the 40s, probably the 50s. And that was a period of time in which some people didn't even take the potential A, they didn't even take this very seriously. I mean, they took E and B they thought were real, but they weren't too sure about A. And this analysis and this experiment made it clear that A was, of course, important. The harmonic oscillator is an example of a quadratic action, of course, and you can then compute what the action of a particular class of a classical path is to go from QA to QB in time TB minus TA. And you can even write down the classical path. It's equal to this expression here. And you can then, well, this, I think, I don't know, I think I was kind of off my rocker when I did this. I think I went into this is very deep into the weeds. The answer is that if you actually do the path integral, you get this expression as being the exactly right answer, but that's kind of complicated, and so I'm going to skip it. What about path integrals in statistical mechanics and effectively lattice gauge theory? Well, there, what we're talking about is e to the minus beta h, which is the Boltzmann operator. So actually the mathematics is much more straightforward, because instead of integrating over lots of phases, we're integrating over simply Gaussians that are damped as you go to, as h goes to higher energies, you're damped out. And the trace of the Boltzmann operator, of course, is what we call the partition function. And here K is Boltzmann's constant, which is roughly 10 to the minus 4 electron volts per degree Kelvin. T is the absolute value of the temperature. Not the absolute value, it's the absolute temperature. And we're going to do the same thing. We're going to use the Trotter product formula. E to the minus beta h is going to be e to the minus epsilon k to the minus epsilon v. It's just that now epsilon is beta over n. So, and remember, beta is 1 over kt. And so we're going to have epsilon be beta over n. So beta is always positive here, and epsilon is always positive, and there are no imaginary factors here. And so the particular integral is like this. You integrate over p prime, you insert a complete set of states, you integrate over p prime, and p prime qa is a phase factor. Ooh, wow, I left out the bra q1. So big, huge typo in 20.61. So this factor here should be there. It's included here because that's how we got this phase factor. Once again, I'm going to write Q1 minus QA as epsilon H bar QA dot, and use the Gaussian integral. Now the I comes not from the action, but from the phase factor of P prime QA and Q1 into P prime. And so we've got to do this integral. This integral is the integral 20.2. And and it's just another Gaussian. And so plugging this into there, what we see is that the first bit of the Trotter product formula is e to the minus epsilon, which is beta over n. Remember epsilon. So this is now an energy term. This is kinetic energy plus potential energy, e to the minus that. So everything's damped. It's much calmer mathematically. And if you put two of them together, well, then you have to do this. And now you have to integrate over Q1. And for arbitrary v, this is not a trivial integral, but we can blithely go from one integral over Q1 to an integral over n minus 1 Qs, and we then have this expression here. So the final result then is that there's a prefactor. There's e to the minus epsilon times the energy. We integrate over all the possible paths. And each path here now is written, is exponentially damped with the classical action, with the classical energy of the path, not action, energy. Each path is weighted. Here I say it's Euclidean action. All right, so it's Euclidean action, but that's Euclidean action is really by its energy. So I'm using the terminology of quantum field theory, but I think that's sort of stupidly pretentious to call it Euclidean action. I mean, it's really weighted by the energy of the path, and what you have then is you can imagine e to the minus beta b minus beta a. That's then given by this integral, and you go from each path is weighted by its classical energy. you can write the Boltzmann operator then as an outer product. And if you want to get the partition function, well, you have to take the trace of this. And so that means you take the trace of this expression and, of course, the trace of QB times anything, some number R times QA is just equal to well, this is an operator actually, is actually QA, the operator R, I'm sorry, QA, the operator R, QB. And, but actually we're taking the trace, and so this is actually QA R QA, and we integrate then over QA. So in other words, we're taking diagonal matrix elements of this operator with the same position eigenstate QA and integrating. And so you get this expression here. So the partition function is then an integral over all possible paths of the energy of that path. And what is the path? Well, the path is a path du going from 0 to h bar beta, or h bar over kt. And in low temperatures, you see, this beta becomes, since beta is 1 over kt, at low temperatures, beta becomes huge. And so the high energy state, if you write it as an outer product, which it is, of course, of energy eigenstates, this thing is a Hamiltonian, and it's a Hermitian operator. You can diagonalize it as eigenvalues En. And so now as you take the limit of the temperature going to 0 or beta going to infinity, you essentially project out on the ground state. And so so the low temperature limit is dominated by the ground state of the theory. The maximum energy density operator is the Boltzmann operator divided by its trace because the trace of a density operator is unity. The matrix elements are the matrix elements of the Boltzmann operator divided by the partition function. And in 3 dimensions, you integrate over paths like this, each path weighted by the energy of the path, classical energy. So for a free particle, what you have is you can actually do this integral, and you wind up with this as the expression. At high temperatures, on the other hand, beta becomes very small, and you basically have something that's given by approximately an path integral of the potential energy and the temperature to the 3 power in 3 dimensions. For quadratic actions, once again, you have a simplification similar to the one we had earlier. And the bottom line then is that the path integral is the path integral of the classical path. And now this classical path is given by a path that's given by the Euclidean equation of motion. So in other words, you have it's the path that minimizes this. And so it's not the classical path, it's a Euclidean classical path. And you then have a correction factor that looks like this. I don't think we have to go through this in detail, but I worked this out some time ago, and one gets these various expressions. I think we can skip that. Now, the next thing to think about is time ordering. If you consider the position operator in the Heisenberg picture at time t, it's given by this expression. And the Euclidean position operator has it replaced by u, or equivalently t is minus iu, or minus I h bar beta, or minus I h bar over kt. And the time-ordered product then of two position operators is the position operator at the later time times the position operator at the earlier time. And you just write it this way. So if Q1 is the later time, it looks like this. If Q2 is the later time, it looks like that. So it's Q of t later times Q of t earlier. And if we're talking about Euclidean expressions, then the Euclidean the analog of the Heisenberg picture in Euclidean time is e to the over h bar q e to the minus over h bar. And so then it's again the Euclidean position operator at the later later instant in Euclidean time. I think I'm going to maybe go through this again tomorrow, not tomorrow, but Tuesday instead of a final exam. Let me sort of skip through this a little bit to get to another point that's less technical but more important, and namely the transition from quantum mechanics to quantum field theory. And basically, this transition is one in which you imagine that instead of 1q and 1p, or 3 q's and 3 p's for a particle in 3 dimensions, you imagine that you've got a large number of q's and p's. In fact, that you have a q associated with every point in space. And then you have a momentum associated with every point in space. And then what people did almost 100 years ago, well, maybe 90 years ago, what they did was impose the same quantum mechanical position. So in other words, if you just have a bunch of q's and the same number of p's, you impose the commutation relations qi pk is I h bar when I equals k and 0 otherwise, and all the q's commute with themselves, all the p's commute with themselves. If instead you have infinitely many q's, one for each point in space, and infinitely many p's, one for each point in space, then you say all of the, you write q as a field, phi of x, and p, the momentum associated with the point in space, as pi of x, a field. And then you say all the pi's commute among themselves, all the phi's commute among themselves. But the commutator of phi with pi is I, and now a delta function. If one imagined that space was if we put space on a lattice, then instead of having a delta function, what we would have here would be a point would be, a lattice point would be labeled by an integer I, an integer j, an integer k, a lattice spacing a. So this position would be a times the 3 vector ijk, and another point would be A times the 3-vector LMN, and you'd then say it was H bar over A cubed times the product of 3 Kronecker deltas. And on the other hand, the phi's and pi's would all commute. So the transition, actually, I should have done this as follows. I should have said, this is quantum mechanics. This is quantum mechanics with infinitely many, but countably infinitely many. And then as you go to continuously infinitely many, you get these expressions with the delta function. You can then say that these phi's have eigenstates phi prime with eigenvalues phi prime, and the momenta have eigenstates with eigenvalues pi prime. And the inner products are products. So these are direct product states, really. You see, the idea here is that phi at a particular point on the state phi prime is phi prime associated with that particular point. Or in other words, written in terms of continuous variables, the idea is that phi of x on the state phi prime is the function phi prime of x times phi prime. And let me just, oh, damn it. Where is this? Hold on. Let me just get this eraser here because I didn't write that very clearly. So it's phi prime at x. Okay. So this is basically what one's talking about, and also pi of x, pi prime is pi prime of x, pi prime. Okay, and then their inner products look like that, and these eigenstates are then complete. Either both the phi prime eigenstate, the eigenstates of the position operator, or effectively the field operator. The outer products give you the identity operator, and the same thing for the outer products of the pi's integrated. The Hamiltonian is then this quadratic expression here. And what's very useful is to go to what are called natural units, where you set h bar and c equal to 1. Actually, I don't understand quite why I mentioned c, since we've been talking non-relativistically. But if one is considering a relativistic theory, then you want to put c equal to 1 also to have fewer symbols on the page. And then you can go through the same Trotter product formula. Namely, now you have the kinetic energy is pi squared over 2 at all the summed over all the points, and the potential energy is, well, whatever it happens to be. And it's everything except for the time derivative terms. Remember, the momentum terms are related to the time derivative of the position. And so all the other terms for the potential are gradient terms, quadratic terms, and then higher terms. I wrote P for polynomial. It could be something that's not a polynomial. It could involve transcendental functions. Anyway, you then apply the Trotter product formula like this. If you're in real time, if you're in imaginary time, you use, in other words, if you're computing the Boltzmann operator, you have an e to the minus epsilon k, e to the minus epsilon v. And what you wind up with is essentially the same thing, namely that the actual amplitude is an integral over all field. If the amplitude to go from one field configuration to another field configuration, and this is really an eigenstate of the fields. To go from that to another one is an integral over all possible fields, intermediate fields, in this time interval, and you weight it by the classical action. And once again, if the process is macroscopic, then the stationary paths, which are the paths whose classical action is stationary, these dominate because they have paths that are infinitely close to them that have almost the same action, and so they come in as with a factor of essentially infinity. On the other hand, the other paths that are non-classical, well, there are a lot of neighboring paths, but they all have actions that are crazily different, so the phases all cancel. All right, well, we're basically out of time. Tuesday at 5:30, I'll resume this and try to make some more of this clear to you. So have a nice weekend. I'm going to stop now.